Welcome back, chemistry students. Today we're going to move into our new unit on nuclear chemistry. So I'm going to share my screen and let's get started. So we're in this new unit on nuclear chemistry, and today we're going to give you the introduction to nuclear radiation. Now, the big idea is that nuclear chemistry is concerned with the structure of the atomic nuclei and the changes they undergo. Whereas in chemical reactions, they involve only small energy changes, nuclear reactions involve much larger energy changes. And so your objective today is to explain how an unstable nucleus releases energy. And this topic actually runs in 3 parts, and you're going to have a recap when we're done. Now, a couple quick things for you. Some 7 tips for study. Make sure you've got your spiral notebook for notes. Have some pens and highlighters. You should have your periodic table of elements available. Make sure you watch this video lesson all the way through and pause as needed. The review slides, when you're looking at those, put them in present mode so you can refine your notes when you go back. Email me any questions you have and complete the assignment on the next tab. And please, only submit work that's been completed. Pressing the submit button to clear it off your screen doesn't do you or me any good. Let's get started. So in this image here, you see a fair amount of pictures. You see the cooling tower of a nuclear reactor. You see an atomic bomb going off in the lower part. You see a scientist doing some experiments, and it looks like you're seeing a big power tube there. And all of this has to do with nuclear chemistry, and today we're going to get into how that goes. So let's do a quick review from our last unit on atomic structure. Let's talk about isotopes. Remember, isotopes are atoms of the same element, meaning they have the same atomic number, and they have the same number of protons, but they have different numbers of neutrons, and thus they have different mass numbers. For example, we have carbon-12, carbon-13, carbon-14. And each of those isotopes are the same element, but a different number of neutrons. And so the atomic number is the number of protons in a nucleus, and this cannot change during chemical reactions. The mass number, that's the number of protons and neutrons in the nucleus of the atom, the mass number is going to change with the isotope. And a quick remember, a shorthand way of indicating the mass number and the atomic number for an atom, you have the elemental symbol. You have the mass number here, which is 12, and the atomic number, which is 6. Remember, the atomic number is not going to change, nor will the protons, nor will the electrons. What will change is the number of neutrons. All right, let's talk about radioactivity. Radioactivity was first observed by Marie and Pierre Curie in the 1900s using uranium atoms. And so a definition of radioactivity is the process by which substances spontaneously emit rays and particles, also known as radiation. So make sure you get that definition down of radioactivity. This is a little video showing how the Curies had identified radiation. I'll play it for you here. You can stop it and pause it as you like. This is from a major motion picture, but it gives you a good illustration as to what went on at the time when they were looking at those peculiar elements.
I want to tell you about radium, the most remarkable, peculiar element, because it does not behave as it should. I measure uranium and I discover less radiations than I do in its all.
You're always more powerful than the element.
Exactly. My instinct is that there is another element skewing the results.
You think you found an undiscovered element?
If you're laughing at me, then I'm not.
That's exciting.
Imagine a grape crushes itself, changes its very being. As the grape turns itself into wine, it releases a powerful surge of energy. Power that can make things happen. You'd be excited, really.
People can see the possibilities. Radioactive matches, radioactive
Cigarettes,
radioactive water, radioactive toothpaste, radioactive beauty powder.
You call this science? As exciting as it seems, radiation is not safe. What have we done?
Many times a discovery, which is originally thought to be beneficial in one way, may not be beneficial in another way, except radiation does have some benefits in some of the different things that we do with it, both for energy and power and in medicine. Well, radioactivity differs from chemical reactions in 6 ways, and let's take a look at those 6 ways. The first way is in a chemical reaction, atoms will attain a stable electron configuration by losing or sharing electrons. Now, when we studied the elements and we started looking at Bohr models, we saw in the valence electron shell that some elements were fully stable when they had a full valence electron shell, and other elements were not. When we move into bonding, you'll see how those elements, when they combine, become stable. But in chemical reactions, atoms will attain a stable electron configuration by losing, giving up, or sharing electrons with other elements. The second way that radioactivity differs from chemical reactions is in a nuclear reaction. The nucleus of an unstable isotope gains stability by undergoing changes. Remember, the isotope is always going to have more neutrons than the original element does. Way 3. Unlike chemical reactions, nuclear reactions are not affected by changes in temperature, pressure, or the presence of catalysts. And we get into our unit on reactions, we'll see that pressure and temperature does have an effect on those chemical reactions, but nuclear reactions are not affected by changes in temperature, pressure, or the presence of catalysts. Type 4, nuclear reactions of an isotope cannot be sped up, slowed down, or turned off. Now, in a chemical reaction, we can speed them up. We can speed up the reaction by increasing temperature, agitation, adding a catalyst. We can slow it down by putting in buffers, as well as dropping temperature, removing agitation, and sometimes you can even turn them off. But in a nuclear reaction of an isotope, it cannot be sped up, slowed down, or turned off. Number 5, unstable radioactive isotopes, also known as radioisotopes, are transformed into stable, non-radioactive isotopes of a different element. And this is what's very different than a chemical reaction. The unstable radioactive isotope, over time, transforms into a stable isotope. Now, the 6th way is radioactive decay. And radioactive decay is the process by which an unstable nucleus emits radiation and energy in order to obtain a more stable state. Remember, most elements are not stable unless they have full valence electron shells. As these elements have different isotopes, they become less stable. And over time with radioactive decay, they obtain a more stable state. So let's review. Nuclear chemistry is concerned with the structure of atomic nuclei and the changes they undergo. Chemical reactions involve only small energy changes. Nuclear reactions involve much larger energy changes. Nuclear reactions are not affected by changes in temperature, pressure, or the presence of a catalyst. And radioactivity was first observed by Marie and Pierre Curie in the 1900s using uranium atoms. And radioactivity is the process by which substances spontaneously emit rays and particles, also known as radiation. All right, update your notes, go into the slides, add into it what you may be missing. Don't forget to update your vocabulary sections. Then open up the next assignment tab for today and respond to the questions on the nuclear chemistry #1 recap. Next lesson that we're going to have is going to be on the types of radiation. Well, that's all I have for you today. I'm Mr. Silverstein. Make sure if you have any questions, you email me and message me and we'll get right back to you. Until next time, you guys have a great day.